So, good morning, participants. Today we are again gathered here on the web platform for the first session of our fifth day of this faculty development program. So today we have eminent speaker from University of Hyderabad, Dr. Chakravarthi Bhagwati. Let me introduce you to the speakers of day. Dr. Chakravarthi Bhagwati is currently the Dean of the School of Computer and Information Sciences at the University of Hyderabad. His research interests are image processing, pattern recognition, and deep learning. He published more than 75 papers in referred conferences and journals. He also works with the School of Medical Sciences in investigating the impact of color vision deficiencies on the ease of use of popular user interface and multimedia design. So Dr. Chakravarthi Bhagwati received his PhD in computer science from Rensselaer Polytechnic Institute, Troy, from USA, and MTech in computer science from University of Hyderabad. He received his BTech in electronics and communication engineering from Jawaharlal Nehru Technological University. He also spent about 5 years working in industry before joining the University of Hyderabad in 1998. Dr. Chakravarthi Bhagwati worked on an OCR system for Telugu and is currently developing an LSTM-driven OCR system for high accuracy on degraded documents. His research scholars are also working on Telugu offline handwritten recognition. He has successfully supervised 12 PhD and more than 100 master students. In addition to his academics, he is a member of Association of Hyderabad Amateur Astronomers also and is an avid amateur astronomer. So now I request Dr. Bhagwati to please address the audience. Over to you, sir.
Thank you very much. It's a pleasure to be here today because Professor Lehal, Gurpreet Singh Lehal, has been an inspiration for many of us here working in the language technologies fields. So it's a great honor for me to be addressing the audience on behalf of Punjabi University, Patiala. So I'll share my video. Let me see if that is doable. Let me just see. So, okay. Let me see what it shows. Oh, 1 second. Let me get this right. So I'll go to share. Oh, I'm already sharing my screen, it says.
Yes, sir, it is visible now.
Okay, so let me then. No, but it's showing a window. I wanted to show the whole screen. Just let me stop sharing and share the entire graph. Now, okay. Because each of these interfaces is slightly different, so that makes it interesting for me. So now I'm what is it showing? I am not able to see what it
You
is
want
showing.
to share the whole screen or you want to share some application?
I just want to show the PDF slides.
Okay, so that was visible earlier.
Okay.
Yes,
Yes.
sir. Okay, now it is visible.
But just let me adjust it so that it's better. But it's showing only the entire window. I wanted to show the presentation view.
Yeah, it is a presentation view.
Oh, it is? Okay. Okay, okay. Because what I'm seeing, oh, what is going on? Okay. Yeah, so is it visible?
Yes, sir. Yes, sir.
Okay. Uh, so I may have to change my layout here to see what I'm showing. Okay. So the screen is visible. So you can see that it is titled Machine Learning for Telugu Experiments in our lab.
Yes, sir.
Yeah. So this is, I was asked to talk about machine learning for Telugu as part of this program, online faculty development program. And so what I thought is that since most of the machine learning work in Telugu in the initial periods had people who are somehow or the other associated with the University of Hyderabad, I'll also talk a lot more about the experiments that we have done and all the work that has happened on machine learning for Telugu from our labs with links to other kinds of work. And of late, there's been a lot of work done with deep learning and machine learning on Telugu. So I thought I'll just give links to those and proceed with that. Now, the talk itself will have three parts. First is the development of the Telugu optical character recognition system as part of this machine learning for Telugu. Then a little bit about Telugu handwritten character recognition, and then the experiments on Telugu text generation. All these three are very important from a language perspective as well as the science and engineering of document image analysis and document processing perspectives. So these three applications together constitute a large quantity of the work that is done using machine learning for Telugu. What I'm leaving out a little bit is the machine translation work, text to speech synthesis, or speech to text, these kinds of things, because today largely Google has overshadowed everyone in those technologies. So I thought it will be much better if I focus on some of the research aspects and the developments happening in the academic world. So let me proceed with this. So this is the first part, which is on the development of the Telugu OCR system. So we started the work somewhere around 2003, and at that time we decided to use a nearest neighbor classifier because that seemed to work well when we tried a few other experiments. And I'll just give highlights of that. That's not the focus. But the second phase of the OCR system is where many of us feel a little disappointed too, because we started working on convolutional neural networks for Telugu in 2007. And if you read all literature on deep learning and the entire revolution that has occurred, the AlexNet convolutional neural network, which was used to solve or at least give spectacular results on ImageNet database, was also developed somewhere around that period. But the paper regarding AlexNet and the entire revolution can trace its path back to CVPR and ICML 2012. So by that time, unfortunately, we had given up on convolutional neural networks. So, but I have no shame. I'm going to show you all the results on our experiments and later what happened. Okay, and then I'll also talk about the Telugu OCR system later on again that we started with deep learning. This was in 2015 that we restarted deep learning work on Telugu OCR system, and we had much better success on that now. And then, yeah, it's a great example of how we need to learn lessons from our failures and successes. So Telugu OCR system, Telugu is the language spoken in the two states, southern states, Andhra Pradesh and Telangana now. But the OCR system, the optical character recognition system, I'm assuming that you know what an optical character recognition system is, but even otherwise, it's simply a computer system wherein you give as inputs document images. So either in TIFF, JPEG, you don't usually like to give JPEG, but generally TIFF, PNG, any of these formats, or even PDF documents, and what you get is as output is text that is usually encoded in Unicode these days, that can be text that can be edited, text that can be reformatted, text that can be put in multiple applications, and so on. So this is what is an OCR. And a typical OCR system functions by recognizing or by breaking down the contents of the document image that we give as input into its constituent parts, all the way down usually to letters and even individual parts of individual characters that we call connected components. And in Indic scripts or Indian scripts, for most North Indian scripts, we don't go down to the level of the connected components. And for most South Indian scripts, we go down to the level of the connected components. The reason for this is very simply that North Indian scripts have this thing, the headline or the so that the characters in a word are joined together by a line at the top. Whereas in the South Indian scripts, each letter is separate. There is no connecting stroke or anything between these letters. So for South Indian scripts, we usually go for connected components. So this is what we had done. The first version, as I said, was nearest neighbor. This is done during the period 2003 to 2006. We recognized the connected components in Telugu. There were about 400 different connected components to recognize in the Telugu script. And the classifier nearest neighbor performed fairly well on good printed text, good quality printed text, giving us a performance of 97% at the character level. But then the performance drops to about 82% if you give images taken from a variety of books. So not all of them need to be of the same quality in terms of the input and so on. So when you do that, the OCR performance suffers. It went down to about 82%. This was the case during the 2003-2006 period. By the way, I'm not sure what the mechanism is for asking questions. Short questions, maybe you can type into a chat box and the organizer can flag me and say that there's a question. Longer questions I'll take at the end of the talk. The Telugu system version 2 developed during 2009 to 2012, not really all the way to 2014, but till 2012. The improvements now really involved making the system more robust so that on variety of inputs it will give roughly similar performance. So now we had a 5,000 page corpus that was created by IIIT Hyderabad. So it's like a third party creation of the corpus. And this is what we divided into training and test sets and tested the OCR on these pages. So recognition is continued to be based on connected components. We now started with improving the nearest neighbor classifier because that was the first scheme, and then moved to convolutional neural networks in 2007. We tried convolutional neural networks between 2007 and about 2011 with varying levels of results. I'll show those results. Then moved to SVM, support vector machines, which gave us the best performance. Okay. So they gave us a performance of 91 to 92% on all kinds of inputs. So this time the input is not restricted to good pages. On good pages, this will give us 98, 99%. On even very bad pages, the performance went down only to about 87 or 88%. Most of the time, the performance was between 94 and 96%. But on an average, over the 5,000 pages that we had, the performance was about 91%. So, as I said, on the same data set, the convolutional neural networks could only touch 85% after a lot of trouble. So we'll come back to this. So here's the slide that I show where we missed a golden opportunity to become pioneers in the world of machine learning. We were the first to try convolutional neural networks for Telugu in 2007. We came up with a very interesting hybrid architecture, and this is one of the master's theses that was published out of our work. One of our students in the lab did this work. I believe yesterday you had a talk by one more of my colleagues, Professor Atul Negi. So Atul Negi and I are partners in crime. We both work together. So many of these things are done by the two of us with one more colleague of ours, Professor Narayan Murthy. So we trained the CNN with 2000 samples. So already you see where the problems are. And the error was greater than 15%. So we regarded it actually as a failure. And we could never really bring it up above this below the 15% error rate. So we gave it up somewhere around 2011. But today, as you know, everything in the world seems to move on convolutional neural networks as a basis. So it is really a sad story. So anyway, let me turn to convolutional neural networks. I'm sure you have done this before, but so I'm not really going to spend any time. So this is done, right? Convolutional neural networks. Yes? See, if convolutional neural networks are done, I'm not going to spend much time. Yeah, so that's right. I'm not going to do much time on, spend time on convolutional neural network because it has been done. And anyway, they're so much a part of the history and the revolution. So that's not what I'm going to talk about. I'll go all the way to our experiments with CNN. Okay. So what we did was we decided to have an architecture that had an input layer connected to a convolution layer. The output is of course a feature map. And the first experiments we did, remember this is 2007 when convolution neural networks were not really popular. So we actually wanted to understand how a convolution neural network works. So what we did was we took a kernel size of 3 by 3 in the convolution layer. And then we trained this. It can even recognize simple things like edges. And what we did was train it on documents where we gave the input as a grayscale document. The output is the same document that was actually obtained by running a standard Sobel edge filter, Sobel filter. Okay? Sobel edge detector in image processing. So the outputs are those. So we trained the convolution neural network on that, and initially we found that the initial weights are all randomly assigned. So the 3 by 3 kernel, you can see in one instance the weights are all totally random between minus 0.25 and plus 0.25. But after training on the Sobel edge detected images, the result of the convolution was learning the Sobel edge detector, which is this -1, 0, plus 1, -2, 0, plus 2, -1, 0. This is a classical Sobel vertical edge detector. So the convolutional neural network did detect these. We were excited at that time because remember 15 years ago, anything and everything was exciting with convolutional neural networks. Okay. Then we tried it with a simple classifier of Telugu letters. So we designed a very simple experiment. Can a CNN separate Telugu characters which have a horizontal edge in them, a horizontal stroke in them, and Telugu characters which don't have a horizontal stroke? Okay. So again, it was a single convolution layer, 3 by 3 kernel, single feature map, a fully connected layer, output. So basically you had an input layer, one convolution layer with a 3 by 3 kernel, single feature map that you flatten out and then connect it to a fully connected layer and then the output layer. That's all. Very, very, very simple network. And training is done with these kind of samples. In all these samples, you see horizontal stroke in the samples here. And in all the negative samples, there are no horizontal strokes. Okay. So these are like the samples. So we trained it on these, and then we found that it was giving about 82% accuracy in separating the horizontal stroke letters and the non-horizontal stroke letters. This is the feature map that it gave us, which is pretty much like an edge detector, to be expected because horizontal strokes can be easily detected using a horizontal edge detector. So it did pick up an edge detector, so you can see the edge detector in play in the feature map. Okay. Then we tried to go forward to recognizing Telugu characters as a whole. As I said, the number of connected samples that we have, connected components, so the number of classes is about more than 400. And we designed a hybrid CNN at that time because we could not really build with the available desktops and others in the school. We really could not train for huge numbers of classes, so we decided to build a hybrid CNN. What this hybrid CNN did is to divide and conquer the 400 classes that you have. So what it does is it recognizes every consonant. Okay, first the consonant. So there are 36 consonants in Telugu. So it will have a 36 class classifier which will identify all the 36 consonants into separate classes. Add to it the 8 vowel classes that we tried, and that made it 44 classes, which take the basic consonants and vowels. Then what we did is we created one more convolution network, CNN, which can recognize all the variations, the matras of a single consonant. Okay, so this could recognize all the matras associated with a consonant. Each consonant usually has about 11 matras. So it will recognize those 11 matras. Okay. So that means we had one neural network which can recognize 44 classes, another neural network which can recognize 11 classes. Right? So together, these two are capable of recognizing 44 times 11, almost 450 classes, which was about the number of connected components that we had in Telugu. So we designed this hybrid architecture, two CNNs in tandem, and the architecture looks something like this. The first CNN is, let me also do this. The first CNN is this one here. So you had the first CNN going here, right? And the second CNN is so this is the first CNN that we had, which takes a 32 by 32 dimensional individual connected component as the input. Then the CNN had these layers. So there's one convolution layer here, followed by a subsampling layer, and there are 4 feature maps. Okay, and this was connected to 2 fully connected layers, giving us an output. This is the architecture which would recognize these individual 44 classes. One such architecture recognized 44 classes, another such same network, similar network recognized 11 classes. Okay. These two were connected together at a later stage. Right? So if we look at the features that were developed by this kind of a network, we find that this is the Telugu character curve. For that, these are the 4 feature maps that the network learned. Okay. So again, there is something which is an edge detector, something which look more at the areas or specific portions of a character. So these curves here, this curve here, this line here, maybe they were taken as important to distinguish between different Telugu characters. But this is what the feature maps look like when you do this simple architecture with layers like these and 4 feature maps. These are the 4 feature maps that we got for the character car. Then the results on some specific things, because we tried multiple architectures. I'm not showing you all the architectures because the architecture too we found was very flexible and convenient for us, so we used that. But here are some simple results on the various Telugu characters listed in the first column here, and the different architectures that we tried, true positives and true negatives. As you can see, the numbers are fairly high out of 200 samples that we tried for each of these. Then we built the complete system here. This is the complete system. So you have as input a 32 by 32 connected component image. Then you can see all these different CNN architectures, the basic building blocks. We took 11 of these. Okay, each one recognizes 44 classes, and there are 11 of these recognizing 450. What is 44 by 11? Yeah, 454 classes totally, and they go into this fully connected 3-layer output, and then you get the output into 454 classes. Okay, so this is the complete classifier. So we built a hybrid architecture where you have individual CNN blocks. Each block recognizes 44 different classes. 11 such blocks together recognize 454 classes through a fully connected layer here. And this was the architecture. This is the 2007, 8, 9 period. And results from this classifier, we found some very interesting things, because we also varied the experiments with a lot of other things. The accuracies range from 99 plus to down to about 73%, depending on the kernel sizes, the number of classes that we fed to each individual block, and then so on and so forth. So eventually we settled on one of these things here with the 95.78 and 96.82% accuracies. So that is part of the background experiments. On multiple fonts, we had varying performance again. Single font, obviously, it gave very, very high accuracy. As we increased the number of fonts, networks became more complex, and accuracies also dropped. But take these accuracies with a pinch of salt, because I'll tell you why we could not get the best performance out of these networks. Okay. So there'll be a lot of time to look at these architectures. Then when we tried this hybrid architecture on the corpus of 5,000 pages, well, we were disappointed. The error stayed around 20%. We were getting a maximum somewhere around 81%. And if we do some careful fine tuning and find those pages on which it is performing extremely badly, remove those pages from the corpus, we have to remove roughly 400 or 500 such pages. Then on 4,500 pages in the corpus, we were getting an accuracy of about 85%. So overall, the performance was not what we wanted to get. Okay, and we really didn't know what the reasons were at this time. These results were from about 2010, 2011 time frame. Okay, so this is just around the time when the University of Toronto group published seminal papers on convolutional neural network. This is just before that time, the publication of those famous papers. So we really didn't know what happened. Okay, so and then because this is part of a large consortium project and there's pressure to show higher accuracies, we decided to put the convolutional neural networks aside, put them on the back burner, leave them to the research part of the students that we have here, and switch to support vector machines. We just borrowed standard SVM library functions, library routines from OpenCV, and we tried this and trained it carefully on the 2,500 or so training images that we had. On the corpus, the error rates came down to about 9%. We were getting 91% accuracy on almost all the 5,000 pages. Average accuracy was about 91% on the 5,000 page corpus. So the SVMs, then we decided to stick to SVM and make it a part of the consortium output. Okay. Any questions? Maybe this is a time when I can spend 1-2 minutes if you have any questions. No? Okay. So this was the first part. Please tell me if you are understanding what I'm saying. If I am not clear about something, immediately ask me, because I'm assuming certain things, because this is the 5th day of the Okay, yeah, that's what I lost the connection somewhere. Can you see me?
Yes, sir. Yes.
Okay. Well, I'm not able to see myself here on the screen. So, yeah. Okay. So, so when did I lose you? I hope you're able to see me now. Yeah. Yeah. So, you're able to see the slides?
Yes, sir.
Okay. So, let me continue. So, as I was saying, the convolution neural networks didn't give us the performance that we wanted, and we decided to go back to SVMs, and SVMs gave us about 9% error, which is almost half that of what we got with convolution networks, and we decided to stick with this. Okay. So if you have any questions now, I can answer them, and then I'll move to our experiments on deep learning OCR. Okay. Yeah. So let me move to that. So now, this is the summary. The OCR was under development since 2003. We explored convolutional neural networks in 2007, did not get good results. The features that we used for the SVM are fringe maps and distances. Fringe maps were highly specialized features that we had for our Telugu script. The error, as I said, was about 9%. And then if we then during that time, we found that testing always on 5,000 pages was a bit of a pain when we wanted to experiment with different architectures. So what we did is we developed a smaller test of 300 pages, selecting them from 5,000 pages. On that, the performance was about error was about 8.3%. So these are almost close enough. So for most of the experiments, we started experimenting with these 300 pages. And then if it works well on these 300 pages, then we'll do the full-blown testing on 5,000 pages. Okay. So this is the OCR story. Then what I did was I went on a sabbatical to University of New York at Buffalo. And that's where one of the big document processing teams is there, headed by Professor Venu Govindaraju. So I went there, and then we tried, during my sabbatical, we tried a deep learning architecture for Telugu OCR. So we went back and looked at an autoencoder based architecture to start with. Again, the inputs are the same, 32 by 32 pixel inputs, connected components. We used a 2-layer autoencoder, with the first layer having 1500 nodes, second layer having 750 nodes. Then the output from the autoencoder was fed into a fully connected MLP layer, and this was having about 500 nodes because um, that's what was the output coming from the autoencoder. Then the output layer was 356 nodes. Instead of using all the 400 plus connected components, we pruned the connected components down to about 356. These 356 connected components covered more than 99.9% of the Telugu corpus. So we use these, and then we train the network on these a deeper, I mean, this autoencoder based network. So the training set now, we also had 200,000 unlabeled samples. See, remember, an autoencoder can handle unlabeled samples. So we started by training this autoencoder with 200,000 unlabeled samples. We also raised the number of labeled samples from 2,500 that we had initially in the school here to about 40,000 labeled samples. In fact, we created afterwards a couple of master students here created a 73,000 labeled sample training data set. And then we use these 200,000 unlabeled samples along with the 40,000 labeled samples to train this autoencoder based network. And what we also did, interestingly, is that we used the earlier SVM based OCR, which remember had an error rate of about 9%, right? So we used that to actually label many samples. So these 40,000 labeled samples, these are not generated manually. A lot of them were generated by using the earlier OCR, which had a 9% error rate. So the labeled samples themselves, initially we allowed them to have errors. Later they were corrected. But this is how we could speed up some of the training set development. And later these 200,000 unlabeled samples and 40,000 labeled samples were used to train the autoencoder based network. In Buffalo, they had this machine which had an NVIDIA Titan GTX 80 card in 2015. So the training took about 5 hours on this card, and we tested on the 300 page subset, and now the error came down to 2.7%. That means the autoencoder based network gave an improvement of almost 6% on the SVMs at this point. Yeah. So this is what happened. Oops. An example of the output is here. I see names there in the audience, some of which could be South Indian names. They may know Telugu. So if there's somebody who knows Telugu, they can read this slide. But for the other people, I'll just say that the number of errors in this is quite small. There are only a few errors. Basically, right at the top, we have errors. Okay. So right at the first word here, we have some errors. And then the error, one more error comes at this place here, which is corresponding to something like that word there. Okay. Other than that, most, I think all the characters are correct in this. This is the output coming from the deep learning based OCR that we developed when I was at University at Buffalo. Okay. So it was a very simple network. So now the question is, why did we fail earlier? The answer to that very simply, now we recognize in hindsight, is that the training wasn't done properly. We had a training set of 2,300 samples, and our CNN had almost 500,000 parameters. So we didn't know how to train the CNN at that time. With 2,300 samples, having 500,000 parameters, there's no way this network could be trained. And CNN either was overfitting the data, there were so many parameters, free parameters for it, it could just do the identity mapping. It just remembered the characters. So on the training side, you'd get very high accuracy. We didn't have enough training samples. Second, we also didn't have enough variety in the training samples. So when we went to Buffalo, there the new training, as you can see, we used a much larger number of samples. Okay. And we also, by that time, learned all about the dropouts and other things that people had proposed. So we used all those to generate much larger numbers. And we also had degraded samples. We knew how to create degraded samples, even incorrect samples. So we gave this much larger variety to the network. So now the network would actually learn. Okay. So it prevented the CNN from just simply remembering what is there at the input and giving us by rote answers, memorized answers. So that's what helped us, the regularization and the dropouts and the much larger numbers. Remember, 200,000 unlabeled samples, 40,000 labeled samples, and that is what helped the network. Okay. If only we knew this before, or if only we had the resources for these things before in the university. I don't think we would have had the resources in 2008 or 9 to do training on 40,000 or 50,000 samples, okay, and train a neural network with that kind of parameters. So this is the story. We failed earlier because of this. So what's the conclusion? Deep learning, yes, as is normally the case now, it helped the Telugu OCR significantly, right? So now there are many variations on deep learning, but for me the most humbling message that came out of this is life is a school of hard knocks. You should persist with your research and then success will come eventually. We actually gave up on convolutional networks, neural networks during 2010-2011 period because that was the same period when another member in the consortium, IIT Madras, had another team working on convolutional neural networks, and they too had very limited performance. So when we all discussed these things, we decided that maybe convolutional neural networks were not the right architecture, and we gave it up at that point. Okay. So this is the end of my first part, where I wanted to talk about the development of the OCR system. Okay. And these are our personal experiences. So if you have any questions on this development of the OCR or the use of deep learning for these OCR systems, you can ask me. And I'll be simple enough sometimes to say I don't know the answers. Okay, but if there are any questions, if there's anything to do with the initial hybrid architectures or the training that we did in the past and the training we do now, anything of that kind, and what sort of training sets do we have now, any of those, I can answer a couple of questions here. I always worry when people ask me nothing, because it means that either I'm completely ununderstandable, or this is something that's already known to all of you and I'm only just repeating something that you knew. Okay, no questions? Are you able to understand what I say?
Yes, sir, we are able to understand.
Okay, very good. Yeah.
We were able to understand, sir, because I'm just new to this topic, and I would want to pursue. This is something which has intrigued me. So probably I will start working on this topic now. So it's too early for me to ask you any questions.
Can you identify yourself? I didn't.
Yeah, sir, this is Mrs. Vidya from Bangalore, sir. I'm an assistant professor in Surana College.
Okay, so this is the.
So this is something I want to do with respect to Canada. So let me probably I will start doing reading and then probably I will.
Yeah. In Kannada, you have the advantage that in IISc, there is a professor by the name A.G. Ramakrishnan,
Okay,
who
sir.
has done a fair bit of work. He also was part of the same consortium where we were developing. So he also used SVM at that time.
Okay.
Yeah, so all of us switched to SVM because the convolution networks. I mean, we tried. Some of us tried convolution neural networks. They didn't work.
Okay.
Telugu group and the Tamil group at IIT Madras, we tried.
Telugu and Kannada script to a large extent they look similar actually.
Yes.
Yeah.
Yes.
Can you please name the repeat the name of the professor, sir, who's worked on that?
A.G. Ramakrishnan.
Okay, sir. Thank you so much, sir. Thank you.
Sure.
Thank you.
Okay. So now the second part is completely different. Now I'll switch to the part where we talk about some of the work we are doing on handwriting recognition, Telugu handwriting recognition. Okay. As you know, in English and many languages now, handwriting recognition is also reached the level of fair amount. I mean, it's a fair success for handwriting, though it is still not perfect. It has reached a high level of success. But for Indic scripts, it is still not the same. Okay, and so therefore we started looking at this, and I'll now show you a few other things. The biggest problem for Indic scripts is the data sets. Okay, we don't have enough labeled data sets, whether it is handwritten or it is printed characters. For printed characters, we've been able to solve the problem in many ways. Now, for many languages, Indian scripts, large printed data sets are available. Handwritten is still an interesting problem. So when we started this, we were looking around for handwritten Telugu data sets. There are only two things that we could find. The first is from HP Labs, and this is actually not for, see, once it comes to handwriting, there are two things in character recognition. The first is called an online character recognition. So this is when you have a pen-based input, a digital pen-based input, where you write on a tablet or on a touch screen, and the actual strokes are captured, the exact directions, the coordinates of the pen tip are captured. Okay, so this is called online. So you actually have the dynamic information of the direction in which you are making the strokes, right? So this is the online. The offline is the traditional thing where you have a handwritten document, you take a photograph of it, then feed it into the computer as input, and you try to recognize. The offline handwritten problem is generally considered a little bit more difficult than the online, because in online you have the extra information in the form of the direction in which the strokes are being made, and also the pen up and pen down give you ideas of connected components and so on. So if you want to split the character into connected components, it is much easier in the online because of the pen movement being captured. Whereas in offline, it is much harder. Okay. So what we did was we searched around and we found HP Labs had a handwritten Telugu character data set, but this was for online. What we did was we took the online characters, just printed them on pages and scanned them so that we don't have the direction information. Okay, because we were looking for offline handwritten Telugu character recognition problem. The total number of characters in this set, I mean connected components in this set, was about 35,000. And the number of classes is only 113. They didn't do all the characters that are possible in Telugu. It's actually a very small set, 113. Then what we did was we directly threw a multi-layer perceptron at it, and we took a training set size of 25,000, the validation set size of 5K, and test set of 5K. Remember, we had 35K. And the accuracy was about 81%, 80.55. Then we tried the same architecture that we had from Buffalo, That's the autoencoder plus the MNP. This time it gave an accuracy of about 81%, 81.2, not very great. Then we created a CNN. CNN had 2 layers, and it's a pure CNN network with an MLP fully connected layer at the end, something like your Lakewood network. So this CNN was like a LeNet 5, and that gave an accuracy of about 90%. So directly a CNN gives an accuracy of about 90%. This was the highest accuracy we could get at that time on the HP Labs dataset. Okay. But now experience taught us something. What is that? Even 35K samples may be too small a training set size. Right? This is experience now at work. Okay. So we decided that we'll have to create or we have to look for better data sets, and if they're not there, actually do them. Right? So we went ahead and anyway, before I get to that story, there is also a comparison at that point. This is work done somewhere around 2017 or so. Okay, 2017-18 time frame, and this is some comparison with the existing things at that time. As you can see that our methods, which are given in bold, are the methods that give the highest performance on the largest test sizes. Okay. The last work they listed there, Pal et al., is from ISI Kolkata, but there the number of classes was much fewer. The number of classes they had was about 40 something. So it gave marginally higher performance than our thing on 113 classes. Okay, so this is what we had at that time. Then we wanted to try a very different approach. Okay. We already have a fairly high accuracy printed character recognition set, right? So we decided that we'll exploit how that printed character set. So we decided we do that, and then what we thought is fine. CNNs and the deep networks are now able to map one kind of input to another kind of input. This is the time when the style transfer papers and other things were getting published, and we decided, okay, handwriting is one style, printed character is another style. So can we do a style transfer from handwritten characters to print? So you give as input a document containing handwritten characters. This network now converts it into equivalent printed character document. That printed document character, once we have it, we'll give it to our old OCR, which gives 97+% accuracy, and then see what happens, right? So we thought this is a kind of a different approach to try than the traditional approach of just looking at the handwriting recognition problem and training networks directly on handwriting. So we came up with this architecture where we have an encoding network that takes the handwritten character image. Let me see if there is any way I can put something to. Yeah. So we have the handwritten image coming here. Okay. From this handwritten image, we send it to an encoder network that gives the representation for this handwritten character. Okay. At the same time, what we have is we also have a network which is trained on printed characters. Okay. So this is the printed character image. This is a pre-trained network now. This printed character image passes to an encoder. That encoder gives an encoding for the printed character. Okay. In the first phase, okay, what we do is we don't have this part here. Okay, this is cut off. So what we have is only this right side network here, which has PC encoding and the PC OCR. So we have the printed character image. There is an intermediate encoding here after the encoder network. This encoded information, the representation, the latent representation of the printed character, is passed to a printed character OCR, which now gives the label. This is the high accuracy printed character OCR right there. Okay, so this is our high accuracy printed character OCR. Right? This is what we have. Then the next phase of training, what we do is we take this handwritten character encoding. We get the encoding for the handwritten characters using the encoder network. And now we put a mapping network in between here. And the job of this mapping network is to convert the latent encoding that I get for the handwritten character into the latent encoding that I get for the printed character. Once this mapping of the latent encoding occurs, the printed character encoding can now be given to the printed character OCR, and hopefully you will get a high accuracy. Okay? Is this idea clear? So this is what we tried. With a mapping network in the middle, because this was the period when this style transfer, mapping networks, encoder, decoder networks, all these were becoming popular. So this is what we tried. Again, interesting things that happen. When we do this, the accuracy we get is only around 71%. Bad news, right? But again, as I said, now we have reached the stage where we are not disappointed with the low accuracy. But as soon as we see this accuracy and a few other things, we know what went wrong. That's the experience from the 2007 to 2011 period and beyond. Okay, so that experience keeps coming into play. So now we know what could be wrong. I'm training it on 35,000 samples. This is a fairly complex network that has three parts, right? The hardware, handwritten character encoding, the printed character encoder, and then the classifier. So a complex architecture, 35,000 samples may not be enough. Fine. So mapping network is not deep enough. There's insufficient data. The approach itself can be wrong. I mean, that always you have to consider because this is research. But then we know that this approach has worked in several other domains, including super resolution and so on. So we didn't want to throw away the approach. We wanted to try deeper architectures. We wanted to try bigger data sets. But then where do I get a bigger data set? So we decided to synthesize a bigger data set from architectures which are called pixel RNN, then pixel RNN plus pixel CNN, pixel CNN plus, and so on. All these which were coming up at that time, and also a GAN. Okay, so this is what happened during this period. So here are some of our results on generating Telugu characters. Okay, so we used the HP Labs initial online character dataset as the source, trained these deep networks for synthesizing characters. Okay, it could have been a GAN, it could have been an RNN plus, because RNNs are also capable of synthesis. You can always look at Chakravarth's blog to see how RNNs can be used for synthesis. So we tried that, and it was generating pretty good handwriting like Telugu characters. These are Telugu characters. It's a single. We also were able to train the network conditionally, so that I say that give me Telugu character with a specific label, right? So A, this is the Telugu character A. You can see that it generates a lot of A's, and they have handwriting characteristics, right? So this is what we did. We further augmented it later with data that was obtained from our Telugu department. The answer scripts, old answer scripts written by the students, we could get access to about 1,000 of those pages. We extracted the Telugu characters from there, and then also tried to train networks to generate handwritten Telugu characters. So this worked well, and eventually we generated labeled data, 225,000 labeled samples using these synthesis networks. Telugu character synthesis networks. So we did this, and now we went back to our mapping network and then tried the mapping network. So the mapping network itself became a lot deeper. There were 5 layers in the handwritten character encoding, 5 layers in the printed character encoding. There were 5 layers in the mapping part, and then the OCR, which had I think 2 convolution layers followed by 3 fully connected layers. 3 convolution layers followed by fully connected layers, and that gave us the full network. But because we have 225,000 labeled samples, we are now able to train this network. And we tried this again with multiple splits in the data sets. And you can see now the accuracy of the handwritten characters through this mapping came up to 90.15%. Okay, the test accuracy was 90.15%, which is on par with the CNN on the much smaller 113 class HP labs dataset. Our synthetic dataset has 350 plus classes. On that, we now achieved 90% accuracy for the handwritten. So this became very, very promising for us. Okay, so this is the kind of experiments that happened to the time just before the pandemic struck. So this is as of maybe December, January 2020, the time when COVID-19 started escaping into the rest of the world. So that's when these were the results at that time. Any questions on this? So now we used a mapping network. So this is like the encoder-decoder networks that we see today in most of the modern deep networks. Okay. So let me show you a few more things. So these are the mapping between printed and other characters. So the top row here in this, the first row, this one here is the handwritten character, and the corresponding second row is the printed character. So it will take a handwritten character, convert it into printed characters. These are on the left side here. So these are the good quality mappings where the handwritten character was correctly mapped to the printed characters. There are some places where we didn't get such a high accuracy. These are much more complicated Telugu characters, and handwriting actually tends to become very poor on these or very interesting on these characters, highly variable. So in some of these, it had mixed accuracy in converting them into printed characters. So that's the reason why there is almost a 10% error at this point in the handwriting recognition. Okay. So now, okay. So any questions here? Because then we'll move to the third part, which is combining this with the text generation from Telugu. Text generation, Telugu text generation. Okay. So now we have a lot more data sets. We've actually made some of the last 2 are data sets that we created. This UHTEL HWCC is for handwriting characters, handwritten connected components. There are 376 classes here. Its size is 75K. And then there is also a much bigger handwritten character data set of 300K size, same 376 classes. This has now, we published it as a paper and made it available from our university website. We are also going to upload it to the IEEE dataset repository in the next few days, so that the handwritten character dataset will be available to all researchers in Telugu handwriting recognition. Okay, so this is the story. So you can see that the big problem initially is that we didn't have datasets. So we had to spend a lot of time creating datasets. Once we created the dataset, we didn't want to do the vanilla, throw a deep network at the problem and solve it. We wanted to try something different. So we tried the style transfer from handwriting to printed. And we're getting an accuracy of about 90%. The nice thing about this is, on a variety of handwritings, it is working with the same accuracy. Okay, so that's the nice thing about it. And I'll just say that for those people who are interested, because I always like to leave something humorous in research. So this is the humor part. In Telugu, there is a very famous poet by the name C. Narayan Reddy. He is popular as Sinare, T. Narayan Reddy, Sinare. And somewhere along in the web, this was the time when we were looking for handwritten samples. We found that some of Sinare's handwritings are available from some website dedicated to Sinare, the C. Narayan Reddy. Fine. We looked at his handwriting and wanted to download. And then when we looked at his handwriting, my God, even human beings can't recognize his handwriting. Okay. If you think the doctors write badly on their prescriptions, all those of you who are interested and know a bit of Telugu in this audience can look at Narayan Reddy's writing, Sinare's writing. I'm telling you, the ultimate challenge I can throw any handwriting recognition researcher is recognize Sinare's handwriting. Okay. Anyway, this is humorous. Don't take it very seriously or get offended by it. But that is the story. So here are some more things. These are all characters that we generated with our networks. So you can see these are very much like handwriting. Okay, and these are valid characters. So these are all nice things that are there in our data set now that we are making available. Now we come to the last part. This is the text generation. Right? We are able to see all these. So what we wanted to do is look at the OCR now. Especially when it comes to handwriting, the problem that we are having is many times even human beings cannot recognize that word. If you just give a word to a human, we saw that with Telugu students here, just giving a word, they could not recognize. It's only when the sentence is given they were able to recognize the word, because the sentence gives the context. This is the way humans work. So we wanted to see if there is a way that our OCR system now becomes human-like and recognizes this way. I know there are now deep networks which recognize paragraphs of text in English, sentences of text in English, and so on. But for me, I actually want to see such systems in action. Okay, I would like to build such a system for our languages and then show it. See, all the results that I'm showing, these are fully tested. We have these systems. The systems are made available. I would like to see this kind of an openness in researchers, and that's the reason why I want to bring these up and make them available openly. So what we wanted to do is see if there is a way to generate text using deep learning, Telugu text, right? And the inspiration, of course, is that famous Andre Karpathy's blog from 2015, where he had a blog which said the unreasonable effectiveness of RNNs. Okay, this is the title of the blog, The Unreasonable Effectiveness of RNNs, where he showed that after training certain LSTM layers and so on, they could output text which was very similar to Shakespearean style when they were trained on Shakespearean text. They could output C programs, almost valid C programs, when they were trained on C programs as input. They could generate LaTeX documents when they were trained on LaTeX input. I tried these on my own with our students in our own labs, and they all work. Okay, we could generate LaTeX documents from my research papers, okay, all generated automatically by these deep networks, these LSTM based networks. So then we obviously asked the question, can we do the same for Telugu script, Telugu text? And very surprisingly, to us it was initially a bit unexpected. It didn't work. We tried the LSTM network. It generated complete nonsense. It could not even generate valid words, leave alone sentences. It was very, very difficult. Then we tried to analyze why it is failing. One answer is that the Indic scripts that we have, our languages, these are so-called Abugida, which is an Amharic or an Ethiopian word. Some people also refer to these scripts as Aksharic, which means that they are based on Aksharas, the alphabet. Our scripts are based on Aksharas. And the alphabet that we have, which is the Varnamala, as we call it, that is not full. It's not complete. If you look at English, every text is made up of that same A to Z letters. There's nothing extra. Or if you want to include the few punctuation marks and the numericals, that's it. That's the text. No other symbols are there in the text. That's not the same with Indic scripts. Our alphabet gives only the basic vowels and consonants, but then our text has combinations of these vowels and consonants, which are not there in the alphabet. So there are vowel consonant units which are from outside the alphabet. When you have a script which has this kind of behavior, where the alphabet is incomplete and the text is generated with symbols which are interpretable as combinations of these basic symbols from the Varnamala of the alphabet, it is called an Abugida script. Some people call it alphosyllabic, some people call it alpho something else, I forget. But the most common names are Abugida, and nowadays people are referring to it as Aksharic, thanks to the word Akshara becoming popular in the language communities. Okay. And what's important with this is, when you give a text document to train our networks to generate text, the text document that you give has an encoding which is not a one-to-one mapping between the text unit that we have and the underlying representation. What do you mean by this? Simply that, see, you have a symbol in our text, right? Something like kya. This kya doesn't exist even in Unicode, right? In Unicode, we write it as ka, the symbol for ka, the Unicode symbol for ka is used. Then you put a halant. Then you put the Unicode symbol for ya. And then you put the Unicode symbol for the a, the long a. Okay, actually the dirgha of the Unicode. So the single akshara kya that we write in our script, right? That one text unit, kya, splits into 4 Unicodes when we have the representation in the text, right? So what it means is there is no one-to-one mapping between text units and the underlying Unicode representation. This adds an extra level of complexity when you want to generate text, if you train it on Unicode, because first the network has to learn which Unicode units go together to form valid text units, higher level text units. These text units, higher level text units, then go together to form words. So you have to find the valid combinations of these higher level text units. They form words. Then the words form sentences. Okay. So there is an extra level of complexity here. Unicode to the character, right? That's the issue. So we soon realized this. And then we wanted to test this hypothesis. It is still a hypothesis. Remember that in science, belief has no meaning. We have to test it. And this is the hypothesis we came up with. So now we designed a multi-layer LSTM architecture. The first layer learns how to form the higher level text units, like yeah, from the underlying Unicode symbols. The second layer now takes these text units and then tries to form words, learn words. Okay? Then the third unit tries, the higher layers forms and learn sentence structures. This is the network we tried. These networks are much more complex. Okay? We wanted to demonstrate something about the complexity introduced by the Abugida script. So we built these LSTM networks and trained them on Unicode. Again, had to painfully create a lot of data sets. And then this is one part. The second part is, remember you are showing only one half of your hypothesis. What's the other half of the hypothesis? If, let us say, even index scripts had a one-to-one mapping between text units and the alphabet, will the simpler RNNs work well? We also have to show that that also works if I have to prove that the problem lies with the Abugida script. So we also now created a new data set where we assigned unique codes to the most frequently occurring 500 aksharas in Telugu, the character combinations of Telugu. Okay, these 500 symbols we found cover about 95% of the corpus. Okay, it's not very high coverage, not even 95%. It's between 90 and 95% of the words in Telugu are covered, which means that if we think of an alphabet which has only these 500 character combinations, then only about 90 to 95% of the words that I see in text can be rendered or synthesized. So we created this 500 character alphabet and again experimented with the simple one layer or two layer LSTM networks. So the first part of this, where we design this multi-layer, it shows the complexity that is required to handle the lack of one-to-one mapping between Unicode and our characters. The second half of the slide here, the bottom part of the slide, this is an experiment which shows that if even index scripts were alphabetic, that is, there is a one-to-one mapping between my text symbols and the alphabet, the simpler networks work. Okay, so we tried both these, and what we found, these are latest results. When I say latest results, these are results which are as new as 3 or 4 days old. So please, I request you not to reveal these or use these in your ideas yet. We are in the process of sending a paper on these, but I thought I'll just show you because at least I strongly believe that ideas should be open among the academics. So we required a highly complex 512 node, 5-layered LSTM network to learn the word generation from Unicode. And then when we looked at the words that it generated, about 90% of the words are valid words. About 10% of the words are invalid. They were not valid Telugu words. So that is the first part. Okay? So the complexity of the Unicode representation on generating text for Telugu is shown here. But I expect that if someone does the same experiment with the other index scripts also, we may find similar results. Because I have not seen even a single paper on text generation using RNNs or LSTMs on index scripts. So then the second part, when we used our 500 character alphabet, I'll have to put quotes around that because this is not really an alphabet, but 500 character alphabet. We could simplify the network. We needed only a 2-layer network which had 32 LSTM nodes in the first and 64 in the second. And the word generation accuracy was also much higher. Almost 97% of the words that this network generates, synthesizes, are valid. So here the training is done on sentences which are encoded in this 500 character alphabet, this artificial alphabet that we created, where there is a one-to-one mapping between the character and the code. So for example, Kya, maybe it received it is the 147th letter in that alphabet. Okay, Kya would be 147th letter. Something like Stra would have been something like 400th letter in the alphabet. So the whole combination itself becomes a single number. Okay. So this is what is done, and I'll show you some of the Telugu that it generated. So these are some of the results that came as recently as about 10 days back or 15 days back. And for those of you in the audience, if there is anybody from the south, if the Kannada person will be able to partially read this. The Telugu person, if there is anyone, they may be able to read this. So they can see that many of the words are valid words. Wherever you see this symbol which says UNK here, unknown, it means that that particular character combination, the symbol combination doesn't have a code in my 500 letter alphabet. So that is the issue there. So it doesn't have a corresponding code. Remember, I used only the 500 most commonly available symbols, and I trained it on a corpus which had all symbols. So these are unknowns. But many of the words are fine. There are a few words which are incorrect. Okay. And one of them is here, which says something like Parukku. Parukku is not a Telugu word. Okay, that's not one of them. There are a few things like that. But the sentences are not valid at all. This is simple 2-layer network to show that we can create words, not sentences yet. Any questions? So I know I'm showing you a lot of research level work here, but these are some of the things that are there. Right. Now after this, so what did we do? This is like the summary now. Then I wasn't sure whether my talk was from 9:30 to 11 or 9:30 to 11:30. So I thought I'll prepare from 9:30 to 11, and then if there's extra time anyway, I can talk about various other things as per the interest of the audience. But what we have done in terms of machine learning for Telugu, I have focused exclusively on document processing. Okay. We started with our work here on optical character recognition systems. This is on printed characters, and showed you how we initially worked on simple nearest neighbor type classifiers, then tried to go to deep networks, then gave up on a convolutional neural network because at that time we didn't have the necessary data sets or the training resources with us, and then switched to SVM, where SVM gave higher accuracies. But then as the convolutional networks made a big impact, and started revolutionizing pattern recognition machine learning field, we decided to go back to convolutional neural networks. Now with better knowledge, larger training sets, more computational power, including GPU machines, multiple GPU machines, high-end GPU machines, we are able to do the required training and show that these deep networks actually have a much higher performance if they actually work. After that, we tried to go to handwriting recognition. And again, as an academic unit, we like to try different ideas. So the idea that we tried is to map handwriting to printed characters, convert handwriting to print, and then see if we can recognize print and therefore recognize the handwritten document. The mapping network again required us to create a lot of data sets, because the data sets are the real bottleneck for research in index scripts. Created some data sets, then worked, created the networks, and we achieved an accuracy of about 90%. As far as we know, this is on par with some of the best results that are shown in the literature for index scripts on the kind of data set sizes that we are training, that we are testing on. Okay. After that, we decided that the way to improve OCR systems and other things now, especially when we come to handwriting recognition systems, is to do something different. Okay. Be able to make the OCR predict sentences. So in order to test that, to predict sentences, we need to have the ability to generate sentences, synthesize text, valid text. So we decided to use LSTMs. Initially tried the simple things, but then very quickly realized that our scripts are different from English, different from alphabetic scripts, and that led to some problems. In order to test the hypothesis that it is the nature of our scripts that's giving us a problem, we designed experiments. And now we have the results from those experiments which make us become confident that it is indeed something to do with the nature of our script that we are having a problem. Okay, so that's what we found now. And I showed you some of the newest results that we have, and I appeal to you not to show these results everywhere, because these are being published in the form of a paper. They're being communicated in the form of a paper. So that's what I have at this point. And thank you, both in English and Telugu, because I was asked to do this in Telugu. I would have loved to say that this word was created by our text generation network, but it is not. It is typed by me. Okay. So thank you very much. And do you have any questions?
Participants, any doubt, any question you can ask from the sir.
I think Professor Atul Negi was there yesterday, right?
Yes, sir.
Yeah. So just want to say that Atul and I, we work together. So
Okay. Yes.
Many of our work share common features. We do research together.
Yes, sir. So yesterday's session was also a beautiful session by Dr. Atul Negi. He explained the CNN network very well to participants, and face-to-face recognition is their task. So
his students and my students, we all do slightly different approaches to using machine learning for Telugu. Atul is the actual pattern recognition background person. I'm more an image processing person who's got into machine learning and deep learning.
Yeah. So I think participants have no doubt. So thank you, Dr. Chakravarti. Thanks for this wonderful session. So the OCR system that you explained, that is really good, and I hope participants have some more information about how to perform the experiments that you have explained in your talk. So thank you very much. Thank you once again for joining us in this session.
Thank you.
Excuse me, sir.
Yeah.
One very layman's doubt I have. Suppose we want to start research in this Indian language recognition, or we I'm just a beginner. So where do we start, or how do we start? If you can throw some light, or
There are two very good references.
okay,
One is a slightly older one. Both these are compilation of papers. So those are edited books.
okay,
The first volume, the older volume, was done by Professor B.B. Chowdhury at ISI Kolkata.
okay, sir.
The second, more recent one was done by Professor Venu Govindaraju at University of Buffalo.
Okay,
Both of these are collection of papers
okay,
and on various index scripts.
okay,
So in one place you'll see all the different things on Indian scripts, the
okay.
work on Indian scripts. They
Okay.
would be excellent starting points.
Thank you, sir. Could you please mention the names of in the chat box so that I can, or I
Yeah,
can.
sure. I'll
Thank
type
you, sir.
that in the chat box.
Thank you so
Because I
much.
don't remember the name of the book, I'm very
No
sorry.
problem. No problem, sir. I thought I will search.
Yeah.
Thank you so much, sir. Thank you.
Yeah.
Okay. Thank you, sir. Thank you very much.
Just let me finish typing this and then do this.
Yeah, sure, sure.
Okay, so I've done that. So thank you very much.
So
Yeah.
we have a talk of Dr. B.B. Chaudhary also in this FDP.
Oh, wonderful.
Yeah.
Yeah.
Dr. Chaudhary interacted with the participants, and he also explained handwriting OCR.
Correct. Yeah. He is one of the real pioneers of this work in the country. Very nice that he also interacted with the audience. I think the audience, the participants of this program should really congratulate themselves that they're able to meet someone of the stature of B.B. Chaudhary.
Yeah, definitely, sir. Definitely. We tried to contact all the eminent personalities that are working in the field of NLP and computer vision. And fortunately, we are fortunate enough that we have the acceptance from all the speakers, and we have a very good session in this FDP.
Yeah. So, okay then.
Thank you,
I
sir.
leave now.
Thank you, sir. Thank you. Thank
Yeah,
you for
thank you very
joining
much.
us. Thank you.